Hello, I'm Juha Mylläri, a doctoral researcher at the University of Helsinki. Welcome to my presentation on discrepancy scaling for fast unsupervised anomaly localization, a paper by myself and Jukka K. Nurminen. So we're going to be talking about anomaly detection and anomaly localization in 2D images. But first, what are these two concepts and how do they differ? Well, in anomaly detection, you'll be looking at an input image and you'll be trying to determine whether the image as a whole is normal or anomalous. If it's anomalous, this means that there's some sort of defect or something unexpected, something that we haven't seen before in the image. On the other hand, in anomaly localization, we'll be looking at the same image, but instead of trying to determine whether the image as a whole is normal or anomalous, we would want to segment the image into normal and anomalous parts. In this research, we're specifically concerned with unsupervised anomaly detection and localization. In other words, we're only going to train our model using normal data, and we're going to assume that we do not have sufficient anomalous data for training the model. Why would this be the case? Well, quite simply, labeling data is time-consuming, especially if you're going to do it on a pixel level. In addition, it may be the case that anomalous observations are rare. You may not be able to find enough of them in time to train your model. Finally, even if you have some anomalous observations, there may be novel kinds of anomalies that you haven't encountered yet. And ideally, it would be nice if your model would be able to pick up on those too. So let's look at a visual example. Here on the left, you have an input image. As you can see, it has some anomalies. So it has two drill holes and a knot. In the center, we see the ground truth anomaly map. So this was created by the annotators of the dataset, and it indicates that there are these three anomalies in these three specific locations. On the right, we can see an anomaly map produced by some anomaly localization model. And you can see that it has correctly identified the locations of those anomalies. All right, so before our research, what was the state of unsupervised anomaly detection and anomaly localization? Well, this has been a very active area of research in recent years. All of the most accurate models for the purpose use convolutional neural networks for feature extraction. Unfortunately, the most accurate methods are computationally quite heavy. But there is, fortunately, a computationally quite light method called student-teacher feature pyramid matching. And our method, discrepancy scaling, builds on this method. So what is this thing called student-teacher feature pyramid matching, or STFPM, anyway? Well, it's a mouthful for sure, but besides that, what is it? Well, it's a very nice unsupervised method for anomaly detection and localization, and no points for guessing, it's based on convolutional neural networks. Specifically, we have two CNNs of identical architecture. One is called the teacher network, and the other is called the student network. And the idea is that the student network learns to imitate the teacher's latent representations of normal images, but not of anomalous images because it doesn't get to see any during the training process. So the teacher network is not going to get trained at all. It's loaded up with weights pre-trained on ImageNet and frozen. On the other hand, the student network is going to be randomly initialized and then trained. Namely, it's trained to try to reproduce the teacher's activations in a certain predetermined set of layers, but only on normal data, because the normal data are all that is going to see in training. And the hope is that after training, in inference, the student is going to be good at mimicking the teacher on normal data, but not on anomalous data. So let's take a closer look at the training process of a student-teacher model. We're going to be feeding in normal images to both networks simultaneously, and the student network is going to try to match the activations of the teacher in a predetermined set of convolutional layers, which I call the designated layers. Unlike in this illustration here, all layers downstream from the last designated layer are going to be discarded because they're not needed. So now that we have a trained STM, how do we do inference on this thing? Well, the hint is in the training, really. recall that for each network, that is student network or teacher network, the output in any designated layer is a 3D array of activations. That is, the array has a width, a height, and a depth. Now, since we're talking about discrepancies between the teacher and the student, you might think that we're simply going to take let's say, the activations of the teacher and subtract them from the activations of the student. And if you guessed that, you'd be pretty close. But actually, there's a slight complication, a certain normalization step, and I'm going to walk you through it. Well, we can think of each width and height coordinate, or each location defined by width and height coordinate, as a pixel of sorts. And the value of such a pixel is a vector of dimension d. Now, what we're going to do is, for each of these pixel vectors, we're going to normalize the pixel vector's length to 1. And we're going to do this for all pixels in both the activations of the student and of the teacher. And then we can go off subtracting one set of normalized activations from the other. Finally, when we then have an array of discrepancies, a 3D array, we're going to eliminate the depth dimension by taking the L2 norm along that dimension. Now, as a slight digression, in the original paper, the authors used a Resonance 18-based STM, which is also what we use, and it happened that in that model there were 3 designated layers, but in a different model there might be more, but 3 in this case. So in each of those 3 designated layers, we're going to take that array of discrepancies that we saw, and as observed, we're going to eliminate the depth dimension by taking the L2 norm. And finally, we're going to take that flat or 2D array and resize it into the size of the original image. This gives us 3 elementary anomaly maps, so to speak, 1 for each designated layer. And the way we're going to aggregate those elementary anomaly maps is simply we're going to multiply them element-wise. Okay, phew, that was the description in very broad terms of student-teacher feature pyramid matching. Recall, this is not our model. What we developed, discrepancy scaling, really starts from here. So the question is, could we take SDFBM but do better in some respect? Well, actually we can. Recall that in the elementary anomaly maps, the anomaly value for each pixel was calculated as the L2 norm of a d-dimensional vector, where d is the depth of the activation array. Well, so far so good. But notice that when we treat this norm of the pixel vector as the anomaly value, we are, as it were, making certain assumptions that may not be met. First, the norm of the vector is, of course, minimized when all elements of the vector are 0. But in actuality, is the expected value of each element of each pixel vector 0? It might not be. Also, a deviation of fixed absolute size is equally significant for each element. But is this realistic? Do all elements have the same variance? It might be the case that some elements just simply tend to vary more than others. Finally, the L2 norm does not take into consideration interactions between elements. But what if some of the elements are correlated? Can we remedy any of these problems? Well, indeed we can. Here's our solution: discrepancy scaling. So to recap, the problem was that not all discrepancies, that is, non-zero entries in a discrepancy array, are equally atypical or equally indicative of an anomaly. That is, some elements of a discrepancy array may have a non-zero mean or normal data. Furthermore, some elements of a discrepancy array may tend to fluctuate more than others. Would it be possible to actually know those element-wise means and element-wise variances of the discrepancy arrays or normal data? Well, fortunately, we do have normal data, that is the training data. So we can do something that's certainly better than nothing. Namely, we can just simply apply the model to our training data and calculate element-wise means and element-wise standard deviations. Then in model inference, when we calculate the anomaly values, we're going to subtract the means element-wise and divide by the standard deviations element-wise. And that's all there is to it. Finally, there was the issue that some elements of these discrepancy vectors might be correlated with each other. Can we do something about that? Well, unfortunately not, because if you think about it, these discrepancy vectors have, or some of them, depending on the designated layer, have a dimension in the hundreds. So estimating these correlations between these elements would mean filling in matrices with tens of thousands of elements. And with limited training data, that's not going to happen. So we simply ignore the correlations. So does discrepancy scaling help? Well, indeed it does. Measured on the MVTech AD dataset, discrepancy scaling improves performance both on the anomaly detection and the anomaly localization task. On the anomaly detection task, the improvement is somewhat modest, but on the anomaly localization task, the improvement is quite significant, and particularly when measured with the area under procurve metric, the improvement is quite large. And in fact, with this metric, discrepancy scaling actually beats even some of those larger and computationally more demanding methods. SDMs are small and fast models, and discrepancy scaling only adds a very small computational overhead, about 1% or so. So why not try ensembling a couple of SDMs? Indeed, if you ensemble two SDMs without discrepancy scaling, you make some gains in accuracy. But if you ensemble two SDMs with discrepancy scaling, the gains are larger. For details, please refer to the paper. We are making the code for discrepancy scaling publicly available on GitHub, so you can run your own experiments, adapt the code to your needs, and export the models that you need. So, I hope you check it out. With that, I thank you for your attention and wish you happy hacking.